As you see from the title, the next topic will be how to intervene on arches or vaults to strengthen them, especially with the idea of reducing the thrust on the vertical structures. Of course, as I anticipated before the break, especially when you cannot use, for example, steel ties that their work is typically of reducing horizontal thrust. These are two classical intervention ideas. They have some drawbacks that I want to discuss with you. The first one you see from the left is if you have problems on an arch, many times you see people that just realize a new slab, okay? A new slab that is supported over the sides with a different independent structure. This is possible. In particular, this is a very, very traditional one because you see also that there is the realization also of a reinforced concrete ring beam all around with all the problems that I don't want to discuss because, of course, we are doing this, you are cutting the masonry, so it is much better not to do a ring beam, but just to go with the individual elements. But this is another issue. This can be done. It is not suggested, for example, if the arch of the vault is particularly thin. Why? Because you know that when you have a curved structure, the presence of a vertical loading is a stabilizing effect, has a stabilizing effect. So if you have an arch and you remove completely the loading, of course this structure will be free. And so you cannot just leave it as it is because there is the risk of falling down. So when this kind of intervention is done, for example, typically the structure is also supported over the arch. The arch is consolidated, for example, and there are some support, some distributed support of the new structure, which can be, for example, a wooden structure, over the arch. So you are able, in this way, to stabilize, of course, the arch itself. Especially, of course, for thin arches, because originally there was of course the weight of the slab, but also the weight of the filling material that was stabilizing the arch. But when you intervene on the arch, very rarely then you put all the material a second time on the arch because you want to reduce the weight. But reducing the weight can give you problems of stability of the arch. So this is what is typically suggested when you do this, to have some other supports all along the arch. Another possibility, and this also is not suggested, at least in the form how it is reported here, but it is important to understand why, is to say, okay, I have my arch, I realize a new curved structure just over the arch or just over the vault. For example, this is a reinforced concrete slab, curved slab, with a thickness, you see, that is comparable with the thickness of the arch. So it can be, for example, 15 centimeters, something like that, 15, 20. I will show you why in a while it is not suggested. And even if, unfortunately, especially in the past, this was a classical way of intervening, because the idea was, okay, I have a new structure and then I still see the vaulted masonry elements from below, but this is the problem that we can have. So if this is our original masonry arch and we have a new structure that will carry all the forces, then the masonry, especially in time, that is after a few months or after a few years from realization of that reinforced concrete slab, will lose the compression forces. Why? Because the stiffness of the reinforced concrete structure is much greater than the stiffness of the masonry, and then the compression of the arch is going from the structure with the lower stiffness to the structure with the higher stiffness. So probably in few months, in few years, you will have that the compression will act only at the level of the reinforced concrete slab, and if you lose a compression in the arch, then you lose stability, for example, against sliding, for example, of the bricks, one with respect to the other one. So, typically we say, this is just one example, typically we say that when we are, especially in an historical building, it is very important that we don't change completely the behavior of the original elements, okay? We must strengthen, but not change completely. For example, here, the idea was to realize a reinforced concrete slab, and the masonry arch of the masonry vault was just an architectural element, okay? But removing the forces can give you problems of stability. Just to remember, when we have an arch, which are the criteria, the things that must be verified for when we have to verify the stability of an arch. First, the importance of the restraints. And because we are considering arches without steel ties, okay, it is very important that at the ends, the vertical structures that we have, can be columns, they can be walls, must be rigid in the sense that they must apply a restraint to the structure. They cannot move, okay? If they start moving, you start having cracks in the middle of the arch, because you have, if you have an arch with a movement of from one side, then it will work as two individual elements that can rotate about typically the center of the arch. So stiffness of the restraints is very important. Then we have to verify the arch against bending and against compressions in the materials. Against the bending, it means that you should remember from the Professor Carloni course, we must have that the resultant of the stresses in a general section must be inside the section of the arch. Okay? So the result can be in any position, but inside the size of the arch or of the vault. Why it must be inside? Because if it is outside, of course you, in order to have stability, you must have compressions, but you must have some tensions. But tension cannot be provided by a masonry, which is a no-tension material. So the force must be in every section inside the section of the arch or of the vault. This requirement can be traduced saying that the curve of pressure must be in the size of the arch at the limit. At the limit, it must be here, closer to the end. Better should be that the resultant is inside the knot of inertia. That is, when it is like this, you have that the compressions, the whole section is under compression. And of course, the stresses will be smaller. But you can have a resultant which is outside the knot of inertia, and then you have a partialized section like this, with still possibility of having stability, but with very much higher stresses, of course, in the masonry, when you start having the section to be partialized. Okay? So inside the section, possibly inside the central part, in order to have everywhere compressions. For example, when we verify against static forces, which are the forces that are acting in a permanent way, we require to have the whole section under compression. When we have seismic forces, we can accept to have partialization of the cross-section. Okay, because seismic forces, horizontal forces, are acting only few seconds. Okay, so we can start having some small cracks, but after the earthquake, it must be the whole section under compression. Of course, then this is a verification against stability of the arch. Then we must verify the value of the stresses, which must be lower than the strength limit of the material. That is, if this is the section or complete in compression or partialized, the maximum value of stresses must be under the strength of the masonry. These are the three criteria that are used to verify those arches. When I reported this possible mechanism, this is of course the most common one. It is the one that I reported here, but this is typical of low arches. For example, of vaults, many vaults. Whereas if we have an arch of different size, of course, the possible mechanisms can be different. These are, for example, three examples. The classical possible mechanism, if you have a round arch, you can have a more complicated mechanism because you have a formation of an hinge here and two hinges, other hinges in other positions here. So the movement will be that this part is going down, these are going up. Or for example, you can have different ones in the case, for example, of ogive arches, which is a quite strange arch, you know, that is coming from Gothic cathedrals, for example. And due to the shape, if the weight is acting, for example, here you can have that this is going inward, and here and here it is going outward. So just to remember that the possible mechanism depend on the shape, of course, of the arches. I just reported the simplest one. When you have movements of the constraints, you start having cracks in vaults or in arches. This unfortunately occurs quite often when we have, for example, porticos without steel ties, because on the side of the wall, here there is the wall. In the side of the wall we have the building, so it is quite stiff on that side. But on the other side here we have the columns, and the columns, of course, without the building, are subject to possible movements, and it is sufficient to have a few millimeter movement, and then you start having, as you see here, cracks on the lower part, just suggesting, for example, that this is the kind of movement that is occurring in this case. Let me go. So, in reality, when we just I wanted to add some comments to those pictures. When these are very simple pictures, because they consider only the presence of the arch, but to consider the real possible mechanism, the real possible movements that can occur, we must consider also the other parts of the structure. For example, this is the arch, but very often over the arch there are some small masonry walls, which are, for example, just the support for a slab. So over the arch there are, let me see if I have another picture, probably I have, but it will be next. That is, over the arch or the vault there are those small depth walls that realize a series of support where wooden slabs, for example, are on, and they are rigid in plan. So the formation of the possible hinges depends also on what you have over it. So it is not that, what I want to suggest you is that it is not just the arch movement, but the arch is a part of a structure with some upper masonries, or, as you see here, for example, the possible movements, for example, also of the walls or the columns, especially when there is some release of the constraints. If we wanted to work with composites, the classical intervention is, of course, you see here, if we start having cracks in the lower part of the arch, what is the simplest idea? Is just to put some composite strips that will carry those tractions on the lower surface. So this is of course, this is the simplest way, and working on the possible mechanism that can occur, you can calculate which is the force, which is the strength that is required at the level of the composite in order to avoid the formation of that mechanism. It is quite similar to the criteria that we had, for example, with the facade movements. You remember? You impose the possibility of a movement, then you calculate which is the force that is required to avoid that kind of movement. So, if we know the shape of the possible mechanism, then the force can be calculated, and then after that calculation, then you can calculate which is the area, which is the width, etc. of the reinforcement. These are some pictures. For example, consider, for example, the picture on the left of a reinforcement which is done from below, exactly with the same criteria of a barrel vault. Of course, if I'm looking at the vault has a length, and what we do is to consider the wall length of the vault, the formation of that mechanism over the wall length, and then we calculate which is the area of the composite which is required to avoid that movement. Then, as an application, we don't put composite over the wall length, but we use, for example, strips at a given distance. And we just use an equivalence, of course, in terms of areas. Okay? So we can substitute a distributed reinforcement with just few strips at a given distance. Of course, the idea is that we must have the same area over the wall length of the vault. So this is an example of application. The picture on the right we will go through after. There is an attention that must be put when we apply the composite on the lower surface. Of course, the idea, I said before, we have the possible crack, okay? This is the masonry. We calculate the force that must be provided by the composite, but that force, remember where we arrived in last class, must consider the possibility of having the bonding, of course. So it is not just the strength of the composite. So the question now is, but if we apply a composite on the lower, in the inner surface, is the strength against the bonding the same as on an horizontal surface? So this is the strength that I have here is the same that I should have if the composite was straight? Unfortunately, the answer is no. Here, because of the curvature, we have a lower strength against the bonding. Why? For the same reason that we discussed before when we have a concave surface. This is the reinforcement. in order to have that we apply a given force, we must be able to carry some traction in the transverse direction, okay, between the composite and the masonry. So we have the masonry, we have the reinforcement, we have attraction forces, okay, vertically. Those forces are reducing the strength against the bonding. So there are rules, and this rule is taken from the CNR document, that are saying that if this is the strength over a flat, straight surface, then we can calculate the equivalent strength against the bonding over a curved surface by reducing by a factor, which is 1 minus, this is the stress that we have orthogonally, this is the strength of the masonry in tension. So the idea is, let me explain better, that we calculate those stresses, we call sigma SD, then we reduce the strength with the reference to the tensile strength of the masonry. So if the tension, for example, is 1/2 of the strength of the masonry, then there is 1 minus 0.5, it is 0.5, and then the strength that we can apply against the bonding is half of the value that we have over a flat surface. Okay? This is an equation that was calibrated experimentally. For example, it is suggesting, and it is true, that if you have a traction transversely, which is at the level of the strength of the masonry, of course you have a failure without having any possibility of transferring force from the composite. Okay? So, when you, of course, those tensions, those stresses depend on the curvature. If you have high values of curvature, then you will have high transverse stresses. Okay? So, for all those reasons, to reinforce an arch or a vault from below is, from the point of view of the formation of hinges, is the straightforward idea, but there can be some problems. For that reason, there is the possibility, but I have to explain to you how, of doing something which is apparently quite strange. That is, applying the composite not on the lower surface, but from the top, you see, on the top of the arch. But I have to explain you why. I will do that in a few minutes. The other possibility, if you still want to do from below, for example, this is typical of masonry bridges. In masonry bridges, for example, you have that shape of the arch, and you cannot go over the masonry bridge, because you have to do this, you have to remove everything of the road, probably can be also 2 meters of incoherent material, etc. So it is typical of operating from below. And if those criteria are not satisfied, there is the possibility of using anchorages to support those attraction forces. So if you have, let me make a better picture. If you have that arch, for example, and you have the composite going like this, you put some anchorages at the given distances, okay, all along, and those anchorages will be those that are put to provide the traction resistance instead of the traction resistance of the masonry. These are the same connectors that same shape that we have seen talking about wrapping, you see. These are some applications, and these are the same connectors that are used also when you want that the strips that you apply are able to transfer traction forces to the other elements, for example. These are in the other positions, of course. I remember you that when you have a formation of openings here, you typically also have the formation of cracks where the vault is supported over the walls, for example. Sorry, on the other side, of course, here. And of course, if you have the composite arriving here, you must anchor it, because you cannot just stop wherever is the formation, the possible formation of the hinge. So anchorages are possibilities. I put also some pictures to show how the anchorages are used, but we have already seen. This is a project. You see, this is the consolidation of an arch structure in a very nice Palazzo Venaria Reale in Turin. Those arches and vaults were very, very long. This is in particular is a Babel vault, very long, because these are 12 meters. And the problem, as you see here, is especially that in the center, the radius of curvature is very long, because in order to have a 12-meter arch, but if you want to have a reduced height, you cannot have 10 meters of arch. Of course, in the center, the radius of curvature will be very small, which is good for anchorage, but it is not good for the behavior of the arch. So reinforcement was required, and for example, here the project required to have one layer of composite all along, plus a second layer here, because here there is the possible formation of the central hinge. Okay, just comments about the anchorages. Of course, the anchorages are very important at the extremities, but this is a picture showing you how this application was studied. And for everything that we have seen, even if at a qualitative level, is typical of vertical forces. It is much more complex, of course, when we have horizontal, possibly horizontal forces, because in the case of horizontal forces, the possible mechanisms are different, and also the positions of the hinges are more difficult to be determined. Why? Because certainly we can have positions of the hinges at the extremities and at the center, but there are usually a position of hinges also in an intermediate position. You see here from the picture of the possible mechanism. And we don't know which is the position of the possible hinge. Okay? So how to calculate those structures? We must use the criteria of the limit analysis. I don't know if with the Professor Carloni you did that. No? But it is the principle is very simple, so it can be explained in few words. There is a huge theory that is supporting it. The idea of the limit theory is that if I have a structure and I don't know where is the formation, the possible formation of hinges, I have to consider all the possible sections and to consider all the possible mechanisms. Okay? The true one, that is the one that will be activated, is the one related with the lower external forces. I think that it was given. I just given in words what is a full theory. So, for example, if I'm considering forces, the forces can be distributed forces due to the weight, for example, but horizontal forces now, because they are the forces related to the earthquake, for example. I don't know where are the possible positions for the hinges. I have to consider all the possibilities, and the one which is true will be that related with the lower action. Also from a physical point of view, this makes sense, because it is all those mechanisms are possible if you think that it is like to have forces that from zero are increasing. Then when you reach a level where a mechanism is formed, then you have failure. Okay, so this is the principle. How to apply in a problem where we don't know the position? Of course, we cannot make an infinite number of calculations, because we must consider infinite possible mechanisms. So what we typically do is to consider at the extremities and in the center, and consider in a position that we try to define by tentative. So we define a position and we calculate the forces that activate that mechanism. Then we change a little bit, for example 1 meter, and we see if the load increases or decreases. If it increases, this is not true, this is the best. So we try to move 1 meter, for example, below, on the other direction. If it is decreasing, then probably can be here or it can be in another position. So we try to, knowing that this is a design procedure, that we don't want exactly the result. So we start from a position which is typically in the, I can say usually from 30 to 45 degrees here, and then we try to move to see if it is going better or worse. So just to explain that in the case of horizontal forces, the position of the hinges is not known and the calculations can be a little bit more complex. This is another picture of a design. For example, here, just a few comments that can be interesting. You see, this is a bridge, and so there are connectors. Here there is written in Italian below, and there are connectors every, let me see, 50 centimeters, it seems to be. So every 50 centimeters, there are those connectors going inside the masonry. And here, for example, the design required 3 strips in the center, the superposition of 3 strips in the center. And so the designers did, instead of having, in order to avoid as possible discontinuities, there was a strip going from here to here, another from here to here, and then the third one here. This is a possibility. The other thing that is interesting is that with the calculation, the longitudinal ones were calculated, that is, the strips that are going, okay, in that direction. These ones, the transverse ones, are not calculated, but they are used to try to have a more homogeneous behavior, some redistribution, possibly, of stresses. Because I remember what I said, let me see, when we were here, that we typically calculate considering that the fibers are distributed everywhere, but then we must use strips. And when you use a strip, it is good to have some transverse fibers that are distributing a little bit the effect of the individual strips. You see the transverse fibers here, and then you see also the same transverse fibers here, these ones, okay? So these are not calculated, but anyway applied. This is the final realization of that project. Okay, what to do instead with always with the composite with cross bolts? You should remember which is the behavior of a cross bolt from previous courses, I think from Professor Carloni. When you have a cross bolt, you have some leading arches, and then we have the bolts. So the most important thing is to reinforce the arches. So the arches are going into the 4 sides. I'm looking at those blue lines, okay? And the diagonal arches are those that are going into the diagonal directions. So these are the areas leading the forces, and they must be strengthened. Then there are the bolts, which are the red parts, which if the arches are stabilized, typically they have no problem. So in fact, you should remember that in a cross bolt, the loading is going on the volt, and the volt is transferring the loading to the arches, which are the supports. So for that reason, the typical intervention is to put the fibers as you see in blue in the right picture, plus, of course, anchorages at the extremities. That is very important because formation of, when you have those arches, you have a formation of a hinge here, but you have also formation of hinges on the upper part here. So here anchorages can be done in different ways. For example, here there are some bars which are steel bars going inside, or for example composite bars as you want. Finally, of course, in order to have that the individual parts of the vault are working correctly, you must transfer the loading the most distributed as possible, and originally probably over those arches there was incoherent material that is removed, and it is substituted with a different structure which is lighter than the original incoherent material. And the classical case is to realize some small brick walls, making a grid of walls and that grid will be then the support for the slab. So of course the total weight is smaller than just putting back all the incoherent material over the vaults, because the weight per unit of masses, per unit of volume is larger because it is a masonry, but the amount of material is much more smaller. Some examples of pictures. The leading parts are these ones and these ones, you see. Okay? These ones instead, or these ones are instead applied for distribution. So even if you see the same size of the strips, because typically you don't change, you don't make smaller and larger strips, but it is very important to understand what is the part of the composite which is really working and which one instead is used to make more uniform the behavior of the vault, of the structure. So the leading ones are these ones, 1 and 2. These ones are instead for have a better distribution. There are other pictures. Here I also put this picture to show you some of the problems that can occur in real applications. For example, here this is not done very, very well, because you see that in order to make a better surface before application of the strip, I don't know if it is possible to see from there, they used a very large thickness of mortar before applying the composite with epoxy. Of course, some regularization is always necessary, because you start from a rough surface typically. So some regularization is necessary, but it is very important that the regularization material is not too thick, because it can be at the end a weak part of your intervention, because its strength is much smaller than the epoxy one. And another interesting thing that you can see from this picture is that unfortunately, sometimes vaults are not very completely regular, because, for example, here there is a hole. Probably it was not a hole originally, because in the past, people, when they realized the vault, they were very careful in having those vaults everywhere. Probably this is, I think, this is where to position a stair inside that probably in the past it was outside of the building. So what is interesting here, even if I know because I was there, that there is, it is not possible to see from the picture. If this is the picture of the area and this is the hall, this is the structure of your reinforcement. There is also a reinforcement all around the hall, like this and like this, whereas there is not the diagonal one, because the diagonal, no, sorry, there is, it is a little bit different, no, it is here, going from here to here, and when there is the hole, it is split in two strips going into the two directions. Of course, it is a more complicated behavior, but I just wanted to remember that in some cases the intervention can be more difficult and they must be calculated. Here instead I put some question marks and I wrote, composites cannot solve any problem. If the surface is very irregular, you cannot think of just applying those strips to solve any problem, or using two strips just because instead of one, just because they are very badly applied. The problem that you have every time that the fibers are not straight is that if you have a traction, let me go here. If you have something like this and you apply traction, where there is a concave surface, you are applying a traction in the transverse direction, okay? And it is very easy that you are breaking the interface. Then if the fibers are straight, they are not able anymore to reinforce. So be very careful with these applications, and some of these problems can be solved instead using FRCM, for example, because with the FRCMs the layer of the cementesis matrix that we are using is much larger, and then it is much easier than to reach a flat surface for the fibers. Or, for example, another wrong application I found here, because there are the fibers over here that are just going like this and without any anchorage. Of course, this can, here for example, you cannot do that for the same reason. Every time you have a concave surface, you are applying tractions in the measure. You can do only with the appropriate anchorage elements. Okay, this is another problem. We are still talking about volts, but thin volts realized just for architectural purposes. They are called in Italian pietre in foglio. Okay, yes.
I have a question on the jurisdiction. Is it a good idea to apply a sort of water on a smooth surface and then apply the...
Here. You can do, but as I said before, when you use FRP work very well with epoxy resin, and if you are using a layer of mortar too high, then that one will be the weak point of your application. So if you must use a large thickness, then it is much better to use FRCM that are appropriate for, because the interface stresses that they require are smaller. When you use epoxy resin, you want to use all the strength of the fibers, and you cannot add a weak surface which is realized by the mold. I was saying thin vaults for architectural purposes. Why? This is typical, for example, of churches, but not only of churches. In some nice palaces, you can find the same solution. That is, you have a wooden roof, but then in the church you see that there is the vault. So the vault is not a structural element, it is just an architectural element. What is the problem? Of course, if you have a vault, you see here, which is not subject to loadings, because it is subject only to its own weight, it is not stable, especially for horizontal movements, due to earthquakes, for example. You see here a picture from a church after the Emilia earthquake, where all the thin wall fell down in the church. Or also here, you see the wooden roof, because all fall down. This is taken, for example, from the earthquake that occurred in Molise 2002. And it is interesting that there are some particular areas of the church which are very vulnerable. If this is the plan of the church, and these are, for example, this is the roof structure, okay, and then this is the vault with this shape. I hope that it is clear. Typically, the failures occur at the extremities, which is quite interesting. You see here it is an extremity of the church. Here also it is an extremity, but not here. It is not a falling down of the wall vault. Why at the extremity is very interesting. And the reason is that, unfortunately, that kind of roof is not stiff in plan, and so if we have an earthquake in the transverse direction, for example, we have a movement of those beams, of those roof elements, okay? But we don't have movement at the extremities because they are the two facades, okay? So, due to the deformability of the roof, this is I'm trying to show you the shape of how the roof structure is moving. The central part is moving, the lateral ones are not moving. And so which are the more vulnerable ones? Of course, those that are subject to shear because of different movements at the two extremities. So these are the more vulnerable part of the church structure. This is another church where I designed the intervention. You see also here at the two extremities of the church. Which are the criteria that can be used? Of course, even if these are vaults, but their behavior is completely different from structural vaults. Structural vaults, we work maintaining the weight. Here there is no weight. So those vaults require some support. And this typical support can be given directly, for example, from the roof structure. This is the design that was done, a roof structure, a substitution, for example, of the original roof structure that you see here, that was a reinforced concrete roof after a bad renovation done 50 years ago. So substitution with a light roof structure with steel elements, for example, and then this structure that you see here is used to support in distributed points, in discrete points, the vault. Okay? Discrete points, of course, because the vault is very thin, it is important that support is most distributed as possible. And this is, for example, what we did. This is another project. The idea is exactly the same. This is the original vault, you see. It is so thin that the designer thought that it was not possible just to have anchorages on a very thin vault. And so the idea was to have some stiffening elements, you see here, in wood, connected in some way with the masonry, and then having some anchorages in given points from the wooden structure to the roof chain, to the roof structure. So, different application, but still the same idea. We use the roof as a supporting structure for a vault because you cannot use the self-weight. These are some details of the same application. You see here all the steel cables that are connecting the vaults which are strengthened because here the thickness was less than 10 centimeters, so you cannot apply just a cable over something that have no weight, okay? So you must strengthen, and then all that strengthened structure is connected with the roof. On the extremities, if possible, stabilizing system is to realize those small masonry wall elements. In Italian we call frenelli, okay? I don't know in English if there is a translation, probably no. This is done, this is stabilizing really significantly the vault at the extremities. Also here, this is stabilizing in compression, but because the masonry is not able to carry traction, there are also, for example, some fibers going all around. So you give compression to the masonry and you give traction to the composite, for example. Okay, so now I like better to stop here because then we have to change the topic.